This video is a video key for 3 spectra problems that were posted on the course website that involve IR given a molecular formula and HNMR and CNMR. So please download those first and work them. I'm going to scroll through some notes on NMR analysis and spectral analysis that we've talked about before, but due to production limitation times, I'm going to be very brief in scrolling through these and then only really explain everything in terms of analyzing the spectra. So we're going to keep this concise as possible. So information from NMR includes integration, chemical shift through the various regions. We need to memorize these ranges. Alkyl, allylic next to the same or on the same carbon as an electronegative element, vinyl, aromatic, and then aldehydes and acids from 10 to 12. Multiplicity, the splitting, singlet, doublet, triplet, quartet, and so forth. Multiplicity is n+1. The number of neighbors that are homotopic or enantiotopic split in the same way. Heterotopic and diastereotopic neighbors split each other differently. So the example seen here, a doublet of doublets, has 2 neighbors of different types. Carbon NMR, we're getting idea about symmetry. Okay, so this molecule has 5 carbons but only 3 signals because of symmetry. And the only time where a molecular formula is wrong is if we have more signals in the carbon than the molecular formula, although do not count a solvent peak for that. Okay, and then we can also check carbon NMR for a carbonyl in the absence of an IR signal. When we label compounds, we label in order of increasing chemical shift. For HNMR, we label A, B, C, D, E, F with letters for each different signal, and we label with numbers in the spectrum for each different signal in the carbon. And then we put those for partial credit assignment onto the structure that we propose at the appropriate position. So let's work 3. Let's find our degrees of unsaturation. So 0 degrees, divide our IR at 1500 and 3000. We see sp3 CH stretch and an OH stretch for sure. No degrees of unsaturation, no rings, no pi bonds. Okay, so for our signals here, A, B, C, D, and E, there are 5 signals in the proton NMR. For number of neighbors, we have 0 neighbors. Although this looks like the OH, it's a broad singlet, so it's the OH, and oxygen doesn't communicate splitting. N+1 is 3, triplet, so 2 neighbors. Here we've got a whole bunch. This is a multiplet. 1, 2, 3, 4, quartet means 3 neighbors, and then 2, splitting into a doublet means 1 neighbor for these. Our chemical shift analysis. 1.5 is the alkyl region, to 2.5 is the allylic region, to 4.5 is the next door to an electronegative atom. So this is a CH2, which has to be next door to oxygen. And it also has 2 neighbors. So we can solve this signal as being next door to oxygen because it's de-shielded all the way into this next door to an electronegative atom range with 2 neighbors. So we've got that much. And then we have another 2 hydrogen with 3 neighbors, and we have a 6H integration. So the only way to have this is to have 2 CH3s together. So if we come out to the right here, we could have one neighbor. That 1 neighbor integrates to 1, so it has to be C as we've labeled it here. And next door to that, we have a CH2, OH. And so we've completely solved the spectrum, putting the electronegative D that we marked there. We know it's next door to a CH2. There's only one other CH2 given, and that's protons that we've labeled B. Three neighbors checks out because we have a CH2 next door to a CH. So this is really not a true quartet. This is also a multiplet where the coupling constants happen to be exactly the same because we've got two heterotopic neighbors. So B is really a doublet of triplets. Single neighbor doublet, two neighbors triplets. So it's a multiplet as well. Okay, but we couldn't figure that out until we put it all together. Okay, so in our carbon NMR, we have 1, 2, 3, 4 signals. Methyls tend to be the least shielded, so 1, and then if we 2 and 3 may be out of order, but we'll just assign them here, and then the most deshielded 4, 1, 2, 3, 4, and we solve our spectrum. So we definitely have this compound as our solution. Fits all of the evidence. No unsaturations, 1 OH signal. Okay, again, degrees of unsaturation, 1 plus 7 minus, or plus 1/2 for the nitrogen, minus 15 over 2. So that's 1 plus 7 minus 7 is 1 degree. Let's see if we can find it in the IR. Draw our line at 1500. There's a CC sharp. Looks like a CC double bond. We have evidence for that with an sp2CH stretch to the left of 3000. We also have some sp3CH stretches. Okay, move on. We've got our evidence for the unsaturation. It's a double bond. Do we have evidence in the NMR? Well, we draw our ranges. And yes, indeed, we have 3 vinyl CHs here. Okay, so there's definitely a double bond somewhere, and since there's 3, we know that we have this relationship where we have the double bond at the end of the line, because that's the only way to have 3 vinyl CH signals. Okay, and so what the integrations are, we really don't know. They're all multiplets because they have diastereotopic neighbors. So I'm not going to try to assign one or the other, A, B, C, D, and E. These signals are all 3 different, so really we have overlapping signals here anyway. Okay, so we've probably got D, E, and F here. They're in the same place though, so it's really hard to assign, but among these 3, we know we've got D, E, and F. Okay, among these 3 at the end. Then we say, okay, well in the allylic region, next door, at close to 2.5, what do we have? So nothing shows up in the allylic region, and there's a reason for that. It's because we've got a nitrogen somewhere hanging out in this molecule. And so if we look at a doublet that integrates to 2 that's directly next to a nitrogen, this would explain it nicely. So C here is explained very nicely, a doublet. So if we count 1 neighbor, here we have 1, 2, 3, 4. So these have 3 neighbors. 1, 2, 3. It's a triplet, has 2 neighbors. C is explained very well by putting it next to nitrogen and in the allylic position next to 1 neighbor. Okay, here's its 1 neighbor that splits into a doublet. And again, just as a reminder, this is a CH2. Now, how do we get a CH6? Well, that's impossible. Okay, so it's got to be 2 CH3s, and then 4 hydrogens here likely are 2 CH2s. And so what we end up having are 2 identical ethyl groups that are both attached to the nitrogen. It shifts, chemical shift into this next door on the same carbon as an electronegative atom. So you end up having symmetry that makes these 2 exactly the same and next door to nitrogen. And then D, E, and F are some combination of those 3. So there is our compound. Now, does it match the CNMR? We would expect to see 1, 2, 3, 4, 5 CNMR signals. What do we see? Sure enough, we have 1, 2, 3, 4, and 5 CNMR signals, with the double bond signals being more de-shielded into that region. So we're in good shape. With our final answer, don't forget to tag the letters like we did above. All right, degrees of unsaturation, same old process every time. 1 plus 9, hydrogens and halogens minus 12 over 2 gives us 10. Minus 6 is 4 degrees. This should scream at us aromatic ring. 1, 2, 3, 4. Very hard to get 4 degrees of unsaturation in a small molecule, but that's one way to do it. Do we have evidence for that in our IR? 1500, draw our line. 3000, draw our line. So we definitely see evidence here of the aromatic overtones, and this CC double bond, very sharp peak sp2ch appears to the left of 3000 sp3ch to the right. Okay, so let's look for more evidence of that aromatic ring. And we have, in our hydrogen NMR, we draw our line. So this is the alkyl region here, the allylic, or in our case here, slash benzylic terminology. Next door to a double bond of a benzene ring shifts to the same place for the most part. So alkyl, nothing. Allylic, we have something to 4.5. We have nothing in this region. And then to the 6.5 to 8.5, we definitely have a dead giveaway, 3 protons in an aromatic ring. Okay, so we've definitely got it in there, and we've got to account for it in our solution. So we have 0 neighbors for these 6, so 2 CH3s with 0 neighbors, and then 2 H's here with 0 hydrogen neighbors, and they're de-shielded into the double bond region. This is the vinyl region, although we can't have a lone double bond in this compound because we're out of degrees of unsaturation. All 4 were accounted for with a benzene ring. So what it turns out, we know that we also have in this compound a chlorine. So we've got some effect of a chlorine next to a benzene ring and a CH2 that's de-shielding this with no neighbors. So what we eventually come to with this is that we have to have the CH2 both next to the benzene ring, and it also must be bonded to the chlorine. So these guys, 0 neighbors, de-shielded way down, okay, into the vinyl region, but actually it's just an effect of shifting to allylic, and then also next door to an electronegative element shifts them even more. And so our protons labeled B here are in this arrangement. Now we have to have 2 more groups on the aromatic ring because we only have 3 aromatic hydrogens. So only 3 of these end up on the ring. So we've got 2 more groups. They are 2 methyl groups, 2 CH3s, 0 neighbors, 6 hydrogens, must be 2 symmetrical methyls. There's 2 ways to make symmetrical methyls given this initial group that we found. We can either put them here, but if we do that, these guys would then become singlets, and we certainly don't have singlets here. Okay, so what we need instead is this arrangement. They still reflect to one another in a plane of symmetry. The chlorine, just rotate that up to here so that it intersects that line straight down through. You can do this with a model kit to prove it to yourself. So the 2 methyls, there they are. They're the, we'll change to red here. A, B is accounted for, and then our aromatic signal C, there's 2 of them, integrates to 2, and then D integrates to 1, and it's a triplet. Okay, very small, couldn't see it, but we don't need that extra information to solve this problem. So how many carbons do we expect to see? Well, let's see. The methyl groups I'd expect to show up first. 1, 1, and then the non-aromatic here, 2, And then the aromatics, who knows what order they're going to show up in, but it'll be 3, 4, 5, and 6 total. 1, 2, 3, 4, 5, and 6 total. So we have the symmetry, we have the solution to this problem as well. It's an aromatic compound, a highly deshielded CH2, symmetrical methyls, and 3 remaining aromatic protons.